It's a pleasure to introduce Professor Po-Lam from the Mathematical Institute at the Australian National University. He's also an adjunct professor at the Chinese University in the city of Hong Kong. He got his PhD under Ellis Stein at Princeton University and then held fellowships at Rutgers University and Oxford before taking up his current positions. He is well known in the field of harmonic analysis, nonlinear analysis, functional analysis, and in particular, he was the recipient of the Ambrosetti-Prodi Medal. The medal recognizes, according to the definition, exceptionally young researchers who have already made outstanding contributions to nonlinear analysis. I've known Po-Lam from my work on Sobolev spaces. In particular, there is a class of spaces that is they are called BY spaces, where the letter Y is in honor of Po-Lam. Today, he will speak about the different class of related Sobolev spaces. So please go ahead, Po-Lam.
So thank you very much for your kind introduction and the kind invitation to give this webinar talk on Sobolev spaces for the wave equations. Yes. This is joint work with Andrew Hassell, Pierre Portal, and Jan Rozendaal. All three of them were at the ANU at the time when we collaborated. Jan Rozendaal has since moved on to Poland for a permanent position. So the idea here is that we will have two different areas of harmonic analysis coming together. One coming from the more classical point of view of Sobolev spaces, where you analyze a function by looking at weak derivatives and also how they interact with little Paley projections. Another coming from a slightly more modern point of view from Fourier integral operators. So ideas about, for instance, Fourier decoupling is going to come in at some point in this talk. Now, we're going to work with dimension n at least 2 today. The one-dimensional case is kind of trivial because we're trying to solve the wave equation, and the solution to the wave equation in one dimension is well known. So in particular, actually, we're going to look at the half-wave propagator, this exponential it square root minus Laplacian for some fixed time t. And here we've got a formula here. The half-wave propagator is the integral of the Fourier transform of f against exponential 2 pi I t times norm c plus x dot c. So of course, if t is equal to 0, then this is just the Fourier inversion formula, and hence you recover your function f. But for t bigger than 0, then this is describing how the function f is going to evolve under this half-wave group. So the function spaces that we're going to introduce is in some way a decoupling space. It decouples the contributions of derivatives in different directions, and you try to measure them in LP where P is not equal to 2. Now, okay, so the rest of the information on the screen that we've kind of talked about. For instance, there is the solution to the Cauchy problem to the wave equation, and the solution can be written in terms of the half-wave propagator and its conjugate, and they behave similarly anyway, so we're going to focus on one of them only today. And for most part, we're going to be interested in fixed time estimates, so let's say t equals 1 to fixed ideas. All right, so using the Pentrel formula, we can see that there's a conservation of energy. The L2 norm is going to be preserved as t changes, because the multiplier that you have here has modulus 1, right? But then the question became more interesting if you ask for the LP norm of the solution for p that is, let's say, bigger than 2. So why do we want to understand LP norms and p is bigger than 2? For instance, if the L2 norm is kept fixed, but let's say the L infinity norm of the solution is big, then intuitively you can think of this solution to the wave equation being concentrated in space at that time. And because let's say the L2 norm is always 1, but you have a very tall peak, then you could think of maybe the support is very small, but the peak is very large, and hence the L2 norm is kept fixed, right? So the only way in which you can have L infinity norm very big, the L2 norm being small, is somehow that the support is going to be somewhat concentrated in space. And this is the same as if you have, let's say, LP norm being big for P very large. So one way of thinking about the question that we're going to describe very soon is to understand whether a solution to this half-wave equation is going to concentrate a lot more in space at, let's say, time t equals 1 compared to time t equals 0. Is it possible that you have a lot of concentration in space at some time after, let's say, t equals 1? So let's look at some examples. I think the example is kind of fun to look at, so maybe we can spend some time with that. This is some way focusing into a single point in space. I'm going to let lambda be a very small parameter that plays the role of a wavelength of a wave. So we've got some wave with very small wavelength and hence very high frequency if you want. So I'm going to have some initial data whose amplitude is equal to 1 along lambda neighborhood of the unit sphere in Rn. So I've drawn, for instance, the initial data on the screen here. I hope you can see that this blue spherical shell, this is supposed to mean a lambda neighborhood of unit sphere in Rn. And F is basically 1 on this annulus, and that's my initial data. Well, the modulus of that is 1. That's what I meant. So F is not identical to 1, but the modulus of that is equal to 1. And it can be arranged in such a way that the solution to this half-wave propagator with initial data F, this U of xt is going to concentrate into a tiny ball of radius lambda after time t1. So this is what happens when t is equal to 0, U is roughly 1 on the spherical shell. It's going to move inside in the direction of the red arrows, and at time t equals 1, it's going to concentrate on a tiny ball near the origin, and this tiny ball is going to have radius lambda.
So I'm sorry. So the interesting part here is not the fact that you start with something that after time 1 becomes concentrated, because there is no arrow of time here, right? But interesting part here is that you start with concentrated data, and after time 1 it is concentrated but in a different place, right? That's
yes. So in a way that well, we're going to compare the concentration at time t equals 1 with the concentration at time t equals 0, right? So in time t equals 0, it's already quite concentrated because it's only on a small neighborhood of the unit sphere. But at time t equals 1, I want to say that this is even more concentrated because it is the volume of the supports at time t equals 1 is just the volume of a tiny ball.
Okay.
Right? So this blue shell has many lambda balls in it, whereas the red dot has only 1 ball, right? So somehow at time t equals 1 is even more concentrated compared to the initial data. But that's a great question. Thank you. So yeah, so I want to see what happens at time t equals 1. Now, if initially the initial data is modulus 1, then I can try to figure out the concentration time equals 1 by using conservation of energy. In fact, this picture is somewhat motivated by, like, maybe the way to think about this picture is that you imagine, let's say you have an explosion in space. So if something that is initially very concentrated near the origin and then explodes, and then the wave propagates away from the, there's the sun wave that is blasting out from the origin, right? So it's concentrated on a thin spherical shell as you evolve in time. And you now take the video of that, you just play it backwards, right? So you take a video of an explosion, play it backwards. This is roughly speaking what happens. And energy is conserved throughout this process. So you can kind of figure out what the amplitude is at every given time. So for instance, if you want just a quick back of envelope calculation, right? You take the energy initially, that will be the height squared times the size of the support, which is lambda, because it's the lambda neighborhood of a spherical shell. which has area 1, roughly 1. And then if you look at the volume at the origin at time t equals 1, the volume is lambda to the dimension, lambda to the power n. So in order for the height squared times lambda to the n to be equal to the initial energy, then the height has to be this negative power of lambda, right? Lambda to the power minus n minus 1 over 2. The precise number is not that important, but this is a negative power of lambda, and that's going to be a lot bigger than 1, the initial amplitude. Right. So is this clear? I hope this is like a good example to keep in mind. Okay, see something in the chat. Oh, you don't think the recording has started? I think it has started. It is, yeah, I think it's recorded, but okay. Yeah, okay, but thank you for checking. Yes, okay. All right, thank you. So yeah, let's keep going a little bit. So I wanted to say that there's another way of understanding the heights at the origin using ideas from wave packets. Some of you will be familiar with that in this audience here. So let's see. Okay, yes. So you could imagine breaking the initial data up into these tiny, well, rectangles in the picture. But what I really meant is that suppose you had a sphere of n-1 dimensional sphere in Rn. One thing you can do is to cover the sphere up by spherical caps. These spherical caps has radius lambda to the power minus 1/2. And then if you take a very thin cylinder with this spherical cap as a base and of height lambda, then you will cover up a lambda neighborhood of the unit sphere. So you take a very thin spherical cap and you thicken it a little bit. This is lambda to the 1/2, and the height here is lambda. Then you will kind of cover up the lambda neighborhood of the unit sphere. This is because the curvature of the sphere works in such a way so that if you go horizontal distance lambda to the 1/2, you're not exiting a lambda neighborhood of the unit sphere. Okay, so these are this is how you decompose your initial data, right? Take your initial data, localize these little cylinders. And this is what I would like to call a wave packet. So schematically, in 2 dimensions, this spherical cap is, of course, there's an interval, and then this is, roughly speaking, what a wave packet is like in 2 dimensions that drawn on screen. But you can also imagine a similar situation in higher dimensions. And the way that the solution to the wave equation works is like you take every initial data like this, and then if you chose your initial data correctly, these wave packets, they're going to actually move just by translation, essentially, and go down to the origin like this. So maybe this initial wave packet is going to move down to the origin just by translation like that. And then the next one is going to move down to the origin, and then it is going to become a wave packet like that, and so forth. So we will have many, many wave packets overlapping at the origin. And these wave packets, they initially had height 1. When they translate, the height is still basically 1. So at the end of the day, if you want to figure out the height at the origin, one simple way of doing this is just to count how many wave packets you have. So there are some constructive interference happening at the origin here in the red dot. And the way that they constructive interfere is just that you add up the amplitudes. If you had the amplitude equal to 1 for each of the wave packets, then you just have to count how many wave packets are arriving at the origin at time t equals 1. And then you will be able to figure out the height at the center. So it is not too hard to figure out how many wave packets you have, because each wave packet is going to occupy basically an area of lambda to the n-1 over 2 on the unit sphere. So this spherical cap has area roughly like that. And then the unit sphere has area 1, so you take 1 over that. So this is another explanation why lambda to the minus n minus 1 over 2 is the correct number of wave packets that you have, and hence the correct heights that you should have at the time t equals 1. Okay, so these are some heuristic calculations.
But this is worst case scenario, right? So
this is the worst case scenario. Yeah, excellent. Yes. Right. So this is the worst case scenario when everything concentrates at the origin. And in fact, this is exactly what I'm trying to say now, right? So if I take the solution operator at time t equals 1, so implicitly t equals 1 here, little t equals 1 here, and I call this capital T. Then in this example, the solution is going to have a much bigger L infinity norm than the initial data. In fact, the solution has L infinity norm basically equal to lambda to the power minus n minus 1 over 2 times the initial data in L infinity. And you can actually work out also what happens to the LP norm if you are a little bit more careful. You can see that for every p bigger than 2, the LP norm is going to be like a negative power of lambda times f in LP. And this negative power of lambda, you can actually compute what the power is. You just start to calculate the LP norm at both t equals 1 and t equals 0, which is not hard at all, because you know the amplitude and you know the support of your wave at both t equals 0 and t equals 1. So the upshot here is that the LP norm is not only be preserved by this evolution of the wave. The LP norm can grow as time t increases. But then the way that it grows, so you cannot expect t to be a bounded linear map from LP to LP. But then if you look at the right-hand side here, the right-hand side here, it is not an LP norm of f, it is some multiple of LP norm of f with the frequency to some power sp. I said that lambda is like the wavelength of the wave, right? So lambda to the minus 1 is like the frequency, and it is like frequency to some power times f in LP. So one way of thinking about it is that you should think of the right-hand side here as a Sobolev norm. So this is really kind of like the W S P comma P Sobolev norm of f. You differentiate the function SP many times, and you take the LP norm. This is one way you can think about the right-hand side, and this is precisely the worst-case scenario for concentration at time t equals 1. Okay. So that's the example that I want to bring about. And how do I know that's the worst possible? Well, because there's the theorem of Peral and Miyachi back in the 80s. So to just set the notations up, I'm going to have HSP being the vessel potential space. I'm going to apply the Rees potential operator of order minus s to LP, and that is what I would call HSP. This is defined for s bigger than or equal to 0, and for p that is strictly between 1 and infinity. If s happen to be a non-negative integer, then this HSP is just what people usually write as WSP, just the s derivative being in LP, s weak derivative in LP. So s equals 1, then it would be really just 1 weak derivative in LP if you look at the Rees potential space, the vessel potential space. All right. And then for p that is bigger than or equal to 1 but finite, I'm going to define s of p to be this exponent here. This is consistent with what I had on the previous screen, except I put absolute value around 1/2 minus 1 over p. But then earlier p was always bigger than 2. Now p is potentially less than 1, less than 2. So the only thing that I want you to know right now is that SP is strictly positive as long as p is not equal to 2, because I'm always in at least 2 dimensions. And the theorem that Peral and Miyachi had independently was that suppose you solve the half-wave propagator up to time t equals 1 and call this operator capital T, then for any P is strictly between 1 and infinity, the LP norm of the solution is bounded above by the HSP, P norm of the initial data. And the example on the previous page says that this estimate is the best possible when P is bigger than 2. You cannot replace SP by anything smaller. Then that would be a false estimate. And then by duality, of course, this is also sharp for P less than 2. So just a little bit of history, what happened after Peral and Miyachi, Seeger, Sogge and Stein, they extended this to more general Fourier integral operators, capital T. And there is also a corresponding result at the P equals 1 endpoint. In that case, you got to define HS comma 1. You define it similarly, except that you apply the Rees potential, the Bessel potential here to not L1, but to a local Hardy space H1. So some Hardy spaces to come in at the P equals an endpoint, as we all know from singular integrals. That's the kind of space to expect. And then Hassell has understood this P equals 1 case by introducing some new function space. And that's the kind of function space I would like to elaborate on today. So that was for P equals 1. Hassell has, in his thesis, some new function space that is explaining why the theorem is true when P is equal to 1. And then Hassell, Po-Lam, and Rozendaal, my collaborators, the three of them, they had developed the theory a little bit more by studying the corresponding spaces when P is strictly between 1 and infinity. So this is actually very nice. This is like a conceptual way of explaining why the results of Peral and Miyachi and also actually the results of Seeger, Sogge and Stein, why these things would hold. There's a very conceptual way of explaining why these things hold, and I'll try to show you a little bit in a second. But just before we do that, I just want to point out that today I would like to also explain a little bit of further generalization of these spaces using ideas from harmonic analysis. And it turned out that they are relevant even if you only care about the classical Sobolev spaces that we are all familiar with. So I feel like that's kind of interesting, and I'll share that with you very soon.
I have a brief question.
Yes.
So in this one point, so this Seeger, Sogge, Stein paper, the generalizations,
Yes.
how general can that be done? Just a brief remark.
It's quite general. So the Fourier integral operators, they have to be non-degenerate, but that's about it.
Mm-hmm. Okay.
Right.
Thank you.
Yeah, thank you. Right. Okay. So Sobolev spaces for these wave equations that I would like to introduce. Now I've got 2 slides to introduce the function space. There are some formulas, but I think it is more helpful to think about them in terms of pictures. So you can read what's on the screen. There's some cutoff function that's identically equal to 1 near the origin. And I want to define some multiplier for each direction omega in Sn-1. So for each omega in Sn-1, I'm going to define some Fourier multiplier that first of all cuts away what happens near the origin. So what is near the origin is cut out, it's not there. And then I want to only look at where the quantity inside is close to 0. So what is this time? In terms of the picture, it's actually fairly easy to explain what that is. So if omega was, let's say, equal to this first coordinate direction E1, then what I should be looking at is this purple region here. This is a parabolic region. And roughly speaking, I want, let's say, C, well, if it's 2 dimension, then it's C2 bigger than equal to the square root of norm C1. Actually, of course not, less than equal to, right? that would be a region like this if it is in 2 dimensions. In higher dimensions, then probably you should replace this by C double prime. So all the remaining coordinates of C is less than or equal to the square root of norm C1. So that's the region that I would like to shade here, except that maybe I should add, maybe I should say 1 plus, just so that's I cut out this tiny little neighborhood of the origin. Okay, so that's the region that I would like to draw, and your function is psi omega is basically supported on this purple region. And then you take something that supported this purple region, smoothly cut off, and then you multiply by this power of norm C. So this power of norm C is going to be like a growth at infinity. It's going to grow like depending on how big your dimension is, but that's the appropriate amount of growth that you want to put on this multiplier. Okay, so like I said, the key feature here is that the psi omega is supported in the parabolic region, pointing in the direction of omega. So if omega is not E1, then you rotate this picture. If omega is here, then there is a corresponding parabolic region that I try to draw on the screen now. But for every direction omega, there is a corresponding parabolic region that psi omega is supported in. And then the size of psi omega is going to grow like a power of norm C. Okay. So for every direction, I've got a multiplier. And the idea about these function spaces is that you should separate the different directions that you have in the frequency space. So here we go. We are going to define LSPQ, where S is bigger than or equal to 0, PQ are bigger than or equal to 1 and finite. And these are the space of tempered distributions G on Rn, for which the following quantity is finite. So the second term is more interesting. Let me explain that first. The first term is kind of like what you need to complete the story, but the second term is the main character at play. So what you do is that first of all, you apply for every direction omega in Sn-1, you're going to apply a multiplier to G, which is psi omega. So what is this? This is precisely psi omega C, G hat of C, and then you take the inverse Fourier transform. Maybe I wrote it in a slightly different notation, but this is really what I meant, right? You take G, take the Fourier transform, localize to the parabolic region using psi omega with this growth, and then once you do that, you take the inverse Fourier transform, and then you compute the HSP norm of your output. So this is a generalization of HSP, except that you localize to that direction. And then after that, you want to somehow average over all the possible directions they have in the Sn-1. So I'm going to compute the LQ norm of the resulting quantity when I take LQ average over omega in Sn-1. And then that is basically what I want to capture in this LSPQ norm. So the LSPQ, the S and P, S refers to number of derivatives. P refers to how I'm measuring integrability in space in Rn. This Q parameter refers to that I'm taking LQ norm on the space of directions. Okay, so that's what this LSPQ is. There's also a low frequency contribution of G in LP. So remember in this psi omega D, I've always cut out the origin, and I now want to put that back in. So this is just the low frequency contribution of G in LP. And then most of the time, we are only dealing with the case when Q is equal to either 2 or equal to P. So
Brief question.
yes.
So the phi, was that bounded? I mean, that was a bounded function, right?
Oh, this phi, yeah, this phi is this initial, the one that's identically near one near the origin, but compactly supported.
Okay. So you
Right.
multiply that in Fourier space, so you're basically smoothing out that part.
Sorry?
I mean, what is this really doing? Because I mean, it seems like you're smoothing out with the phi, right? I mean, you're making a cutoff in Fourier space. So
Right,
you're
I'm making a cutoff in Fourier space and smoothing it out. So this term is going to be extremely smooth because the Fourier transform is completely supported.
and then you take an LP norm. How do you expect to change the LP norm by the phi?
Well, this is a bounded linear operator on LP. So this term is going to be kind of negligible compared to the next term usually, unless your function is really just very smooth already to begin with. So this is like a harmless term. The main term is really the second term.
But you need it. You couldn't.
But I needed to make it a norm, for instance, because otherwise, let's say your function is supported really close to the origin in frequency space, then the second norm is going to be identically equal to 0, because no matter which direction I picked, the multiplier is not going to pick up the contribution of the Fourier transform near the origin.
I see.
Yeah, so I want to make it a norm, right? I want to have a proper norm for my function space. And then close to the origin is kind of difficult to separate the directions. So what we do is that okay, don't worry about the low frequency contribution. The low frequency contribution is going to be very smooth anyway. I only care about the contribution of the high frequency in different directions. Yeah.
Okay.
Right. So that's the moral of the how we want to define this space. Yeah. But thank you. That's a very good point. Yeah. So it's about to say that if I have Q equals to P, let's say LSP comma P, then instead of LSPP, I just write LSP. It's just a little bit easier to say it without the Q. So in fact, the case where Q equals P was already in the work of Hassell, Po-Lam, and Rozendaal. And the case P equals 1 is essentially what Hassell introduced. This is maybe a slightly different way of writing the function space. They do it a little bit differently, but the norms are equivalent anyway.
And normalization condition does not depend on the choice of P, right?
It doesn't depend on the choice of the operator. Yeah. So this is a space.
No, I mean definition of psi omega. You have normalization conditions, right?
Oh, right. So yeah, the psi omega.
Or is it tailored for the two choices, P and 2, or it's general construction? So this, I'm just curious about power n-1/4.
Yeah, that's n-1/4, right? There's power here.
Yeah.
It is the same. It is the same power no matter what P and Q you want.
So what is the significance of this number?
The significance, yeah. I'll say that in a minute. But
okay.
So for instance, the S22 norm should be comparable to the usual what is that? The WS2 norm of your function. So if you okay, so in when P and Q are both equal to 2, what you're doing here, you can use the Fourier transform to analyze the HS2 norm, right? And then in that case, each direction is going to occupy roughly so you're going to calculate, you could normalize all these things, and then you want that to give you the original WS2 norm. So that power turned out to be the right power. If you, well, I mean, it's going to be, it will take 5 minutes to do that calculation here, but that's I think the idea. Right. So normalization has to do with this choice when P and Q are both equal to 2, it has to coincide with the classical Sobolev space. Yeah. Right. Okay. So one way of thinking about this definition is that there is a cotangent sphere, the cotangent bundle, or the cosphere bundle looking at the background. So you should think of x being in Rn, and then omega should be the corresponding direction in the cosphere, in the cotangent bundle based at the point x. So omega, the direction in Sn-1, we've got a point x, but you also care about the direction omega that it is pointing in, and omega is varying on the unit sphere. So this unit cosphere bundle is somehow lurking in the background. And in fact, before the work that I've done with my collaborators, the analysis often goes through the context structure on this unit cosphere bundle. So that's a very nice geometric structure that you can make use of in this analysis. But then that is usually only useful when P is equal to Q. When P is not equal to Q, the structure kind of breaks down because then you're kind of treating X and Q, X and omega somewhat differently, right? One is in LP norm, one is in LQ. And if one is in LP and one is in LQ, it's a little bit harder to use the context structure. But when P and Q are equal, when X and omega are on equal footing, then the unit cosphere bundle is a very useful object to think about. But we won't actually do this today. Okay, so the case Q equals P. Okay, so this is the work of my collaborators. Recall that we have this particular exponent S sub P, depending on dimension and P. So the main theorem has two parts. The first part is an embedding theorem for these LSP. When Q was equal to P, I said we abbreviate LSPQ as LSPP, or LSPP as LSP. So these new function spaces, they are related to the classical Sobolev spaces by these kind of embedding. So LSP embed into HSP, except that you have to sacrifice some number of derivatives. Initially, you have as many derivatives in this space, LSP. Now you have only got S minus SP over 2. So you have fewer derivatives if you want to embed into the regular Sobolev space. On the other hand, if you have many derivatives in your regular Sobolev spaces, then it is already in LSP. So if you have S plus SP over 2 many derivatives in LP in the usual Sobolev space, then you have S many derivatives in the new Sobolev space. So there's an embedding between the original one and the new Sobolev spaces that we want to think about. And then this T, this half-wave propagator, or these more general Fourier integral operators that Seeger, Sogge and Stein studied, they are all bounded on this LSP space. And in fact, there's a way of writing down some kernel bounds for this operator T. And after you lift it to a phase space, this is almost like a heat kernel. It's a very nice kind of integral operator that you have if you write down the integral kernel in terms of the cosphere bundle. So if you combine these two together, you get a really nice explanation about how the theorem of Peral and Miyachi should be proved. You take a regular Sobolev space, you've got embedding into the new Sobolev space, but T is going to preserve your new Sobolev space, and then you got an embedding back into the classical Sobolev spaces. In this process, you sacrifice some number of derivatives, and in fact, if you count the number of derivatives sacrificed throughout the process, it's precisely SP, which is the one that Peral and Miyachi predicted. So if you take S to be SP over 2, then you got the Sobolev space mapping into H0P, which is LP, and then you recover this sharp results of Peral and Miyachi. So I think it's quite nice that they broke this down into conceptually two pieces, one about embedding between function spaces, and another about an invariance of your solution operator on these new function spaces. And then it's very nice that you have invariance of some function space under this Fourier integral operator, because sometimes you don't want to solve the Euclidean wave equation, right? Sometimes you might want to solve a more complicated wave equation, and then you might want to construct the parametrics to those equations. So usually in constructing parametrics, you want to iterate your operator a few times. And if you want to iterate them, you have better have a function space that is invariant under the iteration, so that when you iterate, you still have a bounded operator on those spaces. So in order to create some approximate solution to some more general wave equations, it is nice to have these LSP being invariant under these solution operators, and that's what they have found. Any question about this one?
I think we're good.
Good. Yeah. So yeah, so I just want to now quickly explain what happens when Q is not equal to P. So when you integrate around the sphere, you could also choose to not take the LP norm on the unit sphere. You could choose some LQ, where Q is different from P. And here are the new results that you have when you have Q different from P. So the first result is also an embedding between LSPQ with the classical Sobolev spaces. You have a two-way embedding. So the original classical Sobolev spaces embeds into these new Sobolev spaces after you give up SP over too many derivatives. And this is upon a certain range of Q. So Q equals P will always work, but Q has to be bounded above by some threshold depending on P and 2. And similarly, for the other embedding, the LSPQ embeds into HSP after you sacrifice some number of derivatives, and it works for a certain range of Q. Q equals P was already in the earlier results. So yeah, but then yeah, so there's some mild constraints on Q, but then there are still these embeddings that my collaborator had found. The next one is the one that I found a little bit more interesting. So earlier we were always relating the new function spaces LSPQ back to some classical Sobolev spaces that we know of. But since we have these scales of LSPQ for different S and different P's, you might wonder whether there is a kind of Sobolev embedding appropriate within the scale of LSPQ. And this is the result, right? So you take, so you can ask the following question. So this might be too hard to read, but basically I want to see whether LSPQ can embed into, let's say, L0 and then P tilde Q, where P tilde is potentially bigger than P. This is what would normally happen for Sobolev spaces, right? You have as many derivatives in LP, then it embeds into LP, let's say LP star, right? So some people write it as LP star. LP star should be bigger than P, and how big LP star, how big P star should be bigger than P is depending on S and P and the dimension of the space, right? So we would like to have something like that. And here's the result, right? LS1 P1Q is going to embed into LSP2Q if S1 is bigger than S by this many particular number of derivatives. So maybe it is helpful to look at the classical Sobolev embedding. In fact, I have the classical Sobolev embedding in the next screen, and so maybe I should just go to the next screen, tell you the classical Sobolev embedding, and then come back to this inequality. Okay, so here it is. The classical Sobolev embedding says that HSP1 embeds into LP2 if 1 over P2 is equal to 1 over P1 minus S over N, right? So it's the classical Sobolev embedding that we are familiar with. And you can rearrange this to say that S is equal to N times the difference between 1 over P1 and 1 over P2. So this is the number of derivatives that you need in order to go from LP1 to LP2 in the classical Sobolev embedding. Now we go back to the previous one. In this screen, I'm trying to say that there is, if you want to go from LSP1 to LSP2, the number of derivatives you need to go is to have n plus 1 over 2 times the difference between 1 over P1 and P2. So this n plus 1 over 2 is the amount that you need, depending on the dimension, and times 1 over P1 to minus 1 over P2 to trade how many derivatives you go from LP1 to LP2. this n plus 1 over 2 is actually smaller than the n that you need in the classical Sobolev embedding. So somehow I would like to think of this point number 2 here as an improvement of the classical Sobolev embedding. You need fewer derivatives to go from the new scale of Sobolev space from LP1 to LP2. And that's kind of interesting. Okay. So I would like to just use this previous result to talk about classical Sobolev spaces. I want to refine the classical Sobolev embeddings a little bit, at least in a special case. So the classical Sobolev embedding says that HSP1 embeds in LP2 if P1 is less than equal to P2 and finite, and let's say P1 is bigger than equal to 1, right? And S is this exponent here. Now suppose P1 and P2 are on two different sides of 2. This is an additional hypothesis that I'm putting here. Then I'm going to say that you can explain why this Sobolev embedding is true by the results on the previous screen. So what do? This S, which is n times 1 over P1 minus 1 over P2, can be broken down into the sum of three exponents on the screen, namely SP1 over 2, SP2 over 2, and then the n plus 1 times 1 over P1 minus 1 over P2. These three exponents are what I need to have embeddings on the previous screen. And if I use the theorem on the previous screen, this HSP1, which is the sum of these three exponents here at HP1, LP1, then this is going to have an embedding into this new Sobolev space. As long as I drop S1, I give up S1 many derivatives, I get into these L spaces. I can use the Sobolev embedding in the new spaces to go from P1 to P2. I sacrifice some number of derivatives, in particular this n plus 1 over 2 times 1 over P1 minus 1 over P2. And then once I do that, then I can use the embedding again to go from LS to P2, comma 2, back to LP2. So I was able to use these new function spaces with Q equals 2. So Q is always equal to 2 in this chain of embedding. But then this is like a refinement of the classical Sobolev embedding. The classical embedding can be split up into actually 3 different embeddings if I want. I don't know if it's useful for some other purposes, but that's kind of cute, I find. Okay, but this only works under the constraint where P1 and P2 are two different sides of 2. Because otherwise these numbers don't work out, and that's just a feature of what we found. Okay, so there is also a fractional integration result that we can prove using these new spaces. It is known that this solution operator to the half-wave propagator is then mapped H alpha P1 into LP2 if P2 is bigger than or equal to P1 and alpha is an exponent that depends on what n P1 and P2 are. So if P2 and P1 are equal, then this is the result of Peral and Miyachi. But you can also ask whether or not you can have embedding or have a mapping from H alpha P1 into LP2 and P2 is bigger than P1, and this is the result. You've got sharp values of alpha for all values of P1 and P2. It turned out that there are 3 cases depending on how P1 and P2 behave with respect to 2. If P1 is less than 2 and P2 is bigger than 2, then this is a case that can be explained using Sobolev embedding. And in fact, it's somewhat like what we did on the previous screen. But then there are 2 other cases where, let's say, P1 and P2 are both less than 2 or both bigger than 2. And this result that was known can actually be sharpened using these spaces LSPQ. So I won't go into details with this one, but basically you start with an H alpha P1, you want to end up with HP2. You can apply the embedding theorems a few times, apply an operator T, apply a meta embedding theorem, so that you go from the H alpha P1 space into the L spaces, and then using embedding between L spaces and the invariance of the L spaces under T, you can actually map into now HP2 after a further embedding. So you have an explanation of how these fractional integration results work for the operator T from H alpha P1 to HP2 if you use the embeddings and the invariance theorems that we have for the LSPQ. And it's similar when P1 and P2 are both bigger than 2. Not exactly the same, and I find it curious that this is actually, you will think that maybe duality would do it, but it doesn't. So there's actually a slightly different proof, but in any case, it's also as simple as the one that you have in case 1. So let me not bore you with the numbers. So I would like to just summarize and have a little bit of an outlook of what else one can do. One thing that we saw was that these half-wave propagators, they do not preserve LP if P is big, P is not equal to 2, and the dimension is at least 2. Rather, it only maps some Sobolev space into LP, so you've got to sacrifice derivatives, right? You have sufficiently many derivatives in LP, then your outcome will be in LP. So your initial data has to be sufficiently smooth in order for your solution to be in LP at time t equals 1. And this can be explained by factoring this map from HSP to LP through certain Sobolev spaces LSPQ that is designed for the wave equation. In fact, the idea is to decouple the contribution from different directions, as we saw, right? And then there are embedding theorems between these HSP and LSPQ. And there are also embedding theorems between HSP1Q and LSP1Q and LSP2Q if S1 is bigger than or equal to S2 and P1 is less than or equal to P2. And then the solution operators preserve these LSPQ and Q equals P, and that's the main reason why these solution operators would map these HSP into LP. But this is just, I think, the beginning of a long story. There are many questions that we still don't understand about these new function spaces. I would like to see, for instance, theorems about like the embedding theorem, we prove something, but then there should be other theorems about embeddings that one can prove. In particular, some hypotheses about Q over there, I don't know if they are necessary. You might wonder whether you can interpolate these spaces LSPQ, I don't know. You might wonder whether you can extrapolate or whether or not there are little petty characterizations of these spaces. Like there's quite a bit that one can try to think about. In fact, one thing that I find particularly interesting is that maybe it is calling for study of function spaces that capture not just the little petty projections into analyze, right? So usually one thing that we do a lot in harmonic analysis is that we cut the frequency space up into dyadic analyze, right? So let's say this is 2 to the k, this is 2 to the k plus 1, and then 2 to the k plus 2, and so forth, right? We cut our frequency space up into analyze like that. But maybe one thing that one can do is to not just cut up the frequency space into analyze, but into these sectors as well. So for each, oh, sorry, I actually used j for the frequency variable here. So let's say this is 2 to the j, right? I'm going to, so this is the origin, is also 2 to the j away. So I'm going to cut this analyze up into these sectors, theta jk, where this theta jk is basically a rectangle of size 2 to the j times, so the long side is 2 to the j, and then the short size is 2 to the j over 2, so this is 2 to the j over 2. And then if you're in higher dimensions, then you have many short sides, many sizes, size 2 to the j over 2. So this is essentially a rectangle of that size in the analysis. And then maybe you want to also cut the function up into these theta jk's and then localize them over there. So this is a more refined decomposition of f. And then we might wonder whether or not one can study function spaces using a decomposition like that. Suppose I know something about the delta jkf. What can you say about f, right? Is there a way of building a norm out of these delta jkf, for instance? I think that's an interesting question. And maybe my time is out, so I'll just stop here. Thank you very much.